So we've been looking at motion this semester. We've looked at kinematics, which is the empirical study of motion, and we've looked at dynamics, which is the causes behind the motion, forces and etc. And we've looked at energy and momentum. And these are different ways of looking at translational motion. Well, we wish to also look at rotational motion, motion in a circular sense that is repetitive, something like this. But we can see almost immediately that we're going to have a problem, because if I'm trying to describe the motion of something in a circular sense like this, an object like this wheel, I can immediately see that points of this wheel have different velocities. If I have a point on the rim, it's going through this full circumference of this big circle all the way around in a certain amount of time. But then if I have a point to the interior, it's going around a smaller circle in the same amount of time. So these 2 points are traveling different displacements in the same amount of time. So how can I possibly describe the motion of this full wheel when different parts of it are moving at different linear speeds? That's a great question. And to deal with that, we're going to have to make some new variable definitions. So take a look at this rigid body here. What we mean by a rigid body is a body that is so rigid that it cannot be deformed by forces. So if there's a force on this body, what it's going to do is either move it translationally or make it rotate, but it won't actually change the shape of the body itself. Such a rigid body does not exist in a macroscopic sense, but many things approach this ideal situation. So we have a point on this rigid body, and it's moving through an angle theta, and by doing so it is subtended through an arc length equal to s. So s would be our linear displacement in this sense. And we would know by our definition from arc length that the length s would be equal to the radius of the arc times the angle theta. Or in other words, we can define what we call an angle in radians as being equal to the arc length s divided by the radius of the arc. Hence, 1 radian would be the angle subtended by an arc length equal to the radius of the arc itself. So if this length s were exactly equal to the radius of this circle, we would have 1 radian. If you were a referee and you're calling timeout, you had an arc length like this and a radius like this, and when this arc length is equal to the radius of the arc, we have 1 radian. And hence that angle right there, right about there, is about 57.3 degrees. Here's how we would calculate that. 360 degrees all the way around would be equal to the full arc length around the circle divided by the radius of the arc. That would be equal to the circumference, 2 pi r divided by r, or 2 pi radians. Hence, 1 radian would be equal to 360 degrees divided by 2 pi, 6.28, and that gives us 57.1 degrees. So, that right there, 57.1 degrees, 1 radian. Here are some other common conversions. 360 degrees is 2 pi radians. 180 degrees is pi radians. 90 degrees is pi over 2. 60 degrees is pi over 3. 45 degrees is pi over 4. 30 degrees corresponds to pi over 6 radians. These are all conversions you should know well. At least have them available on your formula card, because we're going to be using radians quite a lot in this chapter. So we say that if we went from one angle, theta 1, to another angle, theta 2, the difference in that angle would be our change in angle, which we call our angular displacement. So our angular displacement, delta theta, is our final angle theta 2 minus our initial angle theta 1. It really doesn't define or matter how we define our origin for these angles, because we're looking at the difference in angles. So the difference will always be the same even if we define our thetas from some other axis. This difference will always be the same angle, the same angular displacement. With this angular displacement, delta theta, we now define an average angular speed as omega with a bar over it, and that is defined to be the angular displacement, delta theta, over the time interval, delta t. If the time interval approaches infinitesimally small, then our instantaneous angular speed, omega, is equal to our infinitesimal change in angle, d theta, over our infinitesimal change in time, dt. So the instantaneous angular speed is the derivative of the angle with respect to time. There's actually a direction for this angular speed, giving us what we call an angular velocity. The direction is given by one form of the right-hand rule. If you curl your fingers in the direction of the rotation, your thumb points in the direction of the angular velocity. So in the case of this rotation, if it were doing this, I would curl my fingers in the direction of the rotation. In this case, the angular velocity is perpendicular to this plane going into me in the negative z direction as we're looking at. If the rotation were going the other way, and I use my right hand rule on that, then the angular velocity would be coming out straight towards you in that direction. So you curl your fingers in the direction of the rotation, thumb points in the direction of the angular velocity. It's the same way a screw would move if you were to turn it one way or the other. If you were to loosen a screw, say going around like this, it will start coming out towards you, and hence that would be the direction of the angular velocity. If you were to tighten the screw, it would be going in towards me, and that would be the direction of the angular velocity in that case. So whatever way the screw would move as you're turning it would be the direction of the angular velocity. We can also define an average angular acceleration, bar over the alpha, as being our change in angular speed over a change in time, and hence our instantaneous angular acceleration is the infinitesimal change in speed in the infinitesimal amount of time. This angular acceleration is parallel to the angular velocity if the angular velocity is increasing in time, and 180 degrees anti-parallel to the angular velocity if the angular velocity is decreasing in time. So increasing in time, same direction as the angular velocity. Decreasing in time, 180 degrees, opposite direction. For our purposes, our angular acceleration alpha will always be a constant quantity. So the average angular acceleration will be the same as the instantaneous angular acceleration. Here's the point though. If we had a rotating body about a fixed axis like this wheel, every particle on this wheel will have the same angular displacement. If I look at a point on the rim and it goes through this angle here, that will be the same angle as a point to the interior going through the same angle. In other words, every point on this wheel, no matter what, will go through the same change in angle as this wheel is rotating. Hence, we finally have a variable, an angular displacement, that describes the whole wheel at one time. Great. Also, the same angular displacement per time will occur as well for every point on this wheel. So we'll have the same angular velocity for every point on this wheel as it's turning, and for that matter, the same angular acceleration when the angular speed changes. So we now have variables that describe the whole wheel, interior and exterior to the rim, that describe the whole wheel at one time, an angular displacement angular velocity, angular acceleration. Wonderful. So with these new variables and these new relationships, the kinematic equations that we know and love from Chapter 2 that deal with linear motion have come back in the form of angular motion. All we've done is replace our linear variables with their angular counterparts. But the form of all the equations is exactly the same. So we have the same kinematic equations. So your task is really to be able to identify what these variables are in a particular problem and then apply them to the corresponding rotational kinematic equation. Let's try it out. A bicycle wheel rotates with a constant angular acceleration of 3.5 radians per second squared. If the angular speed of the wheel is 2 radians per second at t naught equals 0, what angle does the wheel rotate through in 2 seconds? Alright, so we have a bicycle, and when reading the problem, we immediately can identify the angular acceleration. They told us what it was, 3.5 radians per second squared. Now if I were reading this problem and they didn't tell us what it was, I could look at the units and that would tell me what it should be. A radians per second squared has to be the units of an angular acceleration. Then we're given the initial angular speed, omega naught, and that has units of radians per second. That has to be an angular speed with those units. And they ask us what angle does it go through. So we're looking for angular displacement, delta theta, in a time of 2 seconds. So we have alpha, omega naught, t is 2 seconds, and we're looking for delta theta. So with those 4 variables, we choose rotational kinematic equation number 4. Delta theta is equal to omega naught t plus 1/2 alpha t squared. Great. So in this case, our initial angular speed is 2, our time is 2 seconds, our angular acceleration is 3.5, our time is 2 seconds, square that, we get 11 radians. So that is the total angle that we subtend through in 2 seconds. We might be interested in expressing that angle in either rotations or revolutions or degrees. So if we know that there's 57.3 degrees per radian, multiply that by 11, that would be 630 degrees. Or if we know that there's 2 pi radians per revolution, then we multiply it by 1 revolution per 2 pi radians, divide 11 by 2 pi, and we get 1.75 revolutions. So we went once around and then another 3/4. That would be 1.75 revolutions, and that would be 11 radians. What is the angular speed at t equal 2 seconds? Well, if we want the angular speed, omega, at t equal 2 seconds, we know the angular acceleration and we know the time. So by rotational kinematic equation number 1, omega is equal to omega naught plus alpha t. Omega naught is 2, alpha is 3.5, we have 2 seconds. So after 2 seconds, we'll have an angular speed of 9 radians per second. Note, by definition, our linear displacement in the angular sense, linear displacement would be along the arc length, is equal to the radius of the arc times the angular displacement. So our linear displacement can be converted by multiplying our angular displacement, delta theta, by the radius to that point, or the radius of the arc. The tangential velocity is our change in displacement per time, ds dt in this case. And since r is constant as we're displacing along this radius, that would be equal to r times our change in theta per time, which is r times our angular velocity. So we can get the linear velocity of a point by multiplying the angular velocity of the whole object rotating by the radius to that point. And that's why different points on this wheel will have different linear velocities. The whole wheel has the same angular velocity, but a point on the rim has a greater linear velocity because it's r times omega, while a point to the interior will have a lesser r, but the same omega. So they'll have that kind of ratio of linear speeds. And for that matter, the tangential acceleration will be our change in linear velocity per time, r being constant. So r will be r times our change in angular velocity per time, which is r times our angular acceleration. So our linear or tangential acceleration will be equal to the radius to that point times the angular acceleration for the whole wheel. These are our angular to linear relationships. We just take the angular variable, multiply it by the radius to whatever point we're considering, and that will give us the linear variable at that point. How about that? Let's look at another problem. A compact disk in a computer rotates from rest up to an angular speed of 31.4 radians per second in a time of 0.892 seconds. What is the angular acceleration of this disk? So we read the problem, try to identify our variables. We got a time of 0.892 seconds. We're going to have a final angular velocity of 31.4 radians per second, and we start from rest, so our initial angular velocity would be 0. So we have three variables given. Ask for the fourth one, angular acceleration. We're going to choose rotational kinematic equation number 1. Final velocity equals initial velocity plus angular acceleration times time. Our initial angular velocity is 0 because we start from rest. So we have omega is equal to alpha times t. So alpha is equal to omega divided by t. 31.4 radians per second divided by 0.892 seconds gives us 35.2 radians per second squared. That is our angular acceleration for this disk. How many rotations does the disk make while coming up to speed? Well, using rotational kinematic equation number 4, that's going to be our initial angular velocity times time plus 1/2 angular acceleration times time squared, but our initial angular velocity is 0. So it's 1/2 times alpha times t squared, 1/2 times 35.2, 0.892 seconds squared, 14 radians. And if we want revolutions, we need to divide that by 2 pi. So if I take 14 divided by 2 pi, I get 2.23 revolutions. So that would correspond to 2.23 revolutions, or in this case, rotations. If the radius of the disk is 4.45 centimeters, find the final linear speed of a microbe riding on the rim of the disk. We already know the angular speed, so the linear speed of a microbe on the edge would be equal to the radius to that point times the angular speed of the disk. So that's going to be the radius of 0.0445 meters times 31.4 radians per second gives us 1.4 meters per second. We kind of dropped the radians out of the units there because it really is a unitless quantity. So we don't say 1.4 meters radians per second, we just say 1.4 meters per second for a linear velocity. What is the angular speed and the angular displacement of the disk 0.3 seconds after it begins to rotate? Angular speed is our initial angular speed plus alpha times t. We start from 0. That's 35.2 times 0.3 seconds, 10.6 radians per second. Our angular displacement, initial angular velocity is 0. 1/2 times 35.2, 0.3 seconds squared, 1.58 radians. We are going to be looking to extend these analogies from the linear motion to angular motion throughout this chapter. And in that kind of idea, that vein, the centripetal acceleration can be expressed also in angular representation. Our centripetal acceleration is our linear velocity squared over the radius, but since our linear velocity is equal to the radius times the angular velocity, we have r omega squared over r. One of the r's will cancel out, and so we could express equivalently the centripetal acceleration as being the radius times the angular velocity squared. And we might choose to do this later on. That concludes our first short lecture in Chapter 10 dealing with rotational motion.